And this is the first of several lecture segments on closure, one of the most important concepts in JavaScript and related languages. Now, before we illustrate closure, let's look briefly at the latest version of our linked list constructor. This is linked list 4.js. It's derived from the prototypal inheritance example from earlier lectures, but as you'll see here, there are three changes. First, we've removed the drop function just to reduce clutter. We don't need it for this discussion. Second, the apply function has been renamed to forEach to match the name of a similar function of array at which we'll be looking. And then third, there is a mapEach function that's very similar to forEach, except that, as you can see, it does call a function on each data value, passed in as a parameter, their action, but it uses the returned value of the function to replace the data value. Thus, the function is a sort of map in the mathematical sense. It converts the linked list from one set of data values to another via calls of action. Now, an essential prerequisite to understanding the workings of closure is comprehending the runtime stack, RTS, and stack frame concepts from languages like Java and C. Closure is tied closely to the management of stack frames or their JavaScript equivalent. A review set of lectures from a standard C course is provided as a resource. Read it and understand it, or read and understand equivalent material before proceeding. As a reality check, we'll have a series of in-lecture questions here, and please answer them. And if you can't answer them, then be sure to at least read the RTS transcripts, even if you don't have time to listen to the lecture recordings that go with them. These in-lecture questions reflect the level of comprehension that you have to have on the RTS in order to start understanding closure. So, perhaps after some review on your part, here's question 1. If there are two local variables, call them local 1 and local 2, and they're in two different functions, say f1 and f2, and this is C or Java, might they occupy the same location in memory? Not at the same time, of course, but might they occupy the same location at two different times in memory? And if so, how might that happen? And coming back from a pause, if the two different functions are called in succession from the same caller, so we call f1 and then f2, so that each has stack frames occupying the same area of the runtime stack, then it might be that the memory areas for local 1 and local 2 would coincide. So question 2. If they do occupy the same location, would they do so every time? Or might they sometimes do so and other times not? And if the latter, how? Again, coming back from a pause. Well, it all depends on where the stack frames for f1 and f2 are. If, for instance, f1 calls f2, or perhaps f1 is called after a different sequence of parent calls than an earlier call of f2, then their stack frames will be in different spots, and so will their respective local variables for those calls. In question 3. So, what exactly happens to a local variable when its owning function returns in C or Java? Is the local variable erased? Could I retain a pointer to it, at least in a language like C that has pointers? Coming back again from a pause, the variable continues to exist, but it's in a part of the runtime stack that is above the top of stack, and is thus technically garbage. And the variable is vulnerable to being overwritten at any time by another function call, so retaining a pointer is definitely not reliable. It would be a bug. Okay, so let's look now at the code for total.js down here. Now, this sets up a linked list, 3 elements, with content 114 and 42 in that order because of the way the push works or the add works. And it reports the sum. It does that by calling forEach on the list and passing it a function whose action is to total up each value into the variable total and then report the sum. Let's run it briefly here. So running total.js. Total is 156. So that's looking pretty good. But something kind of interesting is going on here. Let's call the big function, starting on line 3, the outer function. And the one created on line 9 here, the inner function. Now, total is a variable of the outer function, not the inner function. the outer function doesn't even directly call the inner function. It calls for each, which in turn calls the inner function. So apparently the inner function is reaching back across two call boundaries to modify the total local variable of the outer function, as we can indicate in an RTS diagram here, and be sure you understand this diagram. We have the call of outer, which we were looking at. It calls for each. That calls the inner function, which is reaching back to the outer's stack frame to modify the total. Now, this doesn't seem impossible. The stack frame of the outer function call exists during the for each call, and so does total. But as we'll see in later examples, it gets more complex. So consider now the adder.js file. We start by setting up sample linked list object right here, as before. But there is a faster way to do it than all those add calls. We create an array of 3 numbers by constant array declaration, and then call its for each function. It's fine to call functions on array constants like that, by the way. They're legitimate array objects. Now, array.prototype.forEach does the same thing for an array that our for each does for our linked list. It calls the passed function once for each array element. And here's that closure concept again, because the inner function passed to for each is adding each array element to list, which is, of course, a local of the outer function. The result is a quick initialization of list to contain those 3 elements, though note that they'll be in the opposite order from the array because list.prototype.add does a push to the front of the list. It doesn't add to the end. Okay, now that list has some data, let's try the map_each method, transforming each data element in the list to a new value. We'll create a function adder that adds an increment to its parameter and returns the sum. And passing this to map_each, as we do, should increase each data element. And so the for each call on line 13, which is just printing the changed linked list, confirms. Actually making it run here. There's adder.js. 110, 24, and 52. We increased each element from what it was, and remember they're in backward order, by 10. So it worked as advertised here. But note how we created the adder function. We called makeAdder, passing the amount by which we wanted to increment, the 10. So makeAdder is an outer function that creates and returns an inner function, which we referred to by adder. And as before, the inner function may access the parameter, inker, of its outer function, makeAdder. Parameter is really a form of local variable that gets initialized. But inker was, note the past tense, a parameter of the now returned makeAdder function. It should cease to exist upon makeAdder's return. How can the adder function keep referring to it throughout the call of linked list dot map_each? In a conventional language like C or Java, this would be impossible. But under JS closures, an inner function may continue using the local variables and parameters of the outer function in which it was created, even if the outer function has returned. This is a remarkable feature, and as we'll see in the next lecture segments, it allows many interesting designs, all of which involve creating a function object that retains some or all of the locals and parameters that existed when it was created. And in the very next segment, we'll look at how this feature is actually implemented using the JS runtime stack, and the idea that a JS stack frame might actually exist for longer than the running time of the function call to which it belongs.